Hi, this is lecture 5 of the MEC 3820 heat transfer course for the summer of 2020. I'm going to start breaking these lectures up into individual parts to keep them at a manageable length. So from last class, we looked at, or rather we developed the last video, we should be saying, we looked at the formulation of the heat diffusion equation, and I'm putting it up here. This is the full form for the one-dimensional unsteady case. So if we simplify it to make it a steady state case with no internal energy generation, this term goes away. This is for the internal energy generation, and the unsteady term goes away as well, so it equals 0. So we end up with a second order boundary value problem. And as we stated, that since we're taking, it's a second derivative, so if I take the derivative of something and that equals 0, then that something has to be a constant. So we end up with dt dx is equal to a constant. So we have a second order ordinary differential equation. We kind of know what the answer is going to be, but let's go ahead and formally solve it. So we have to separate our variables. That's our first step. And then we integrate both sides. The right-hand side is 0, so integrating 0 gives me a constant. So then we're going to separate our variables once again and integrate once again, and we end up with our solution, right? So Tx, the temperature as a function of x, is equal to this unknown constant C1 times x plus C2. And what we then do is establish some boundary conditions. So if we want a particular solution to this second order boundary value problem, we need to impose the boundary conditions. And in this case, for this particular solution, we will use the boundary conditions where they're constant temperature. So at x equaling 0, we'll say the temperature of the surface is Ts1, and at x equaling L, the temperature of the surface is Ts2. So if we go ahead and then evaluate this, our general solution, at x equaling 0 and let it be equal to Ts1, we of course will find that the value for C2, this unknown constant, will equal Ts1. Now we can then utilize the value for C2, which is Ts1, again put it back into our equation, and now solve for the equation at the other boundary condition. So we'll say T at x equaling L is going to equal Ts2. And that's going to allow us to solve for C1. So C1 is going to be basically, well, it's going to be a gradient, right? It's Ts2 minus Ts1 over L. We take those two constants, put them back into our general solution, and this becomes our particular solution for heat transfer through a slab, a one-dimensional solid object where the walls are being held at different temperatures. And this, again, the particular solution to the ordinary differential equation, which is the heat equation, is the solution for T, so how T varies as a function of x within the solid. So we now have our particular solution for the temperature distribution, right, in the plane wall, subject to constant temperature boundary conditions for the steady state case with no internal energy generation. That's a mouthful, but that's what this equation represents. So in this case, I can now assign some values. So let's let Ts1 equaling 225 degrees T, Ts2 equals 85 degrees C, and the thickness of the wall is 0.3 meters. So we take that and we plug it all into our particular solution, and we end up with an expression for T. And just to point out that the slope is negative here. So this is exactly what the temperature profile would look like in the wall. So now again, note the units here. So the vertical axis is temperature, and the horizontal axis is the position within the wall. X equaling 0 is the left-hand wall, right? We then know its left-hand value is 225 degrees. The right-hand side is at 0.3. This is the temperature of the right-hand wall, which is specified to be 85 degrees. And then our particular solution says that we have a linear distribution of temperature between those 2 points. So now if we return to Fourier's law says the heat rate is going to be equal to minus Ka ddx of the temperature, right? So we have a value for the temperature. The temperature for this particular solution is what's just appeared there in those brackets. So if I take the derivative of it, we're going to find out, right, the derivative of this constant term is 0. So we end up with minus Ka Ts2 minus Ts1 over L, which gives us minus Ka dt, or delta T over delta L. And I like to use Kelvin for these particular situations because I did warn you, isn't this where we started from? Right? So we did a lot of work to get back to our original hypothesis, which was Fourier's initial observation, right? The empirical observation was that the heat rate through a solid object is equal to delta T over delta L. The only thing that we've done in developing our heat equation is that we've actually shown exactly how the temperature varies within the block, and indeed we find out that it is a linear situation. So just summarizing, for the particular solution where where the surfaces are kept at individual temperatures, we get the heat rate is equal to minus Ka delta T over delta L. We can then write this as a heat flux, which we're going to use the value of, or the notation little q dot is equal to minus K delta T over delta L. Now, where we're headed to this now, we're going to start looking at different ways of solving these problems, essentially for a plane wall and a composite plane wall. And we're going to keep dealing with situations where we have a delta T over a specified length. So what we're going to end up doing most of the times is actually dropping the negative sign and just assigning the hot temperature to be Ts1 and the cold temperature to be Ts2. And again, I like to throw Kelvin in here because, you know, it starts driving you nuts. Like, we took a lot of time to discuss why this negative sign was here, and now I'm telling you to quote unquote ignore the negative sign. But that's not what we're really doing. We're saying that we now know enough that energy and the heat rate and the flow of thermal energy is going to be from a region of high temperature to a region of low temperature. And so once we know this, we can essentially simplify the way we're going to be looking at problems. And I'll pick this up in the second part of this lecture.